Hello guys and welcome to today's class. Today we will look very quickly at the last subtopic of the topic 3.3 energy. Okay, so this is energy part 3, which is the law of conservation of energy. I will explain very briefly as I can the concept so that you can start working on two or three problems. Okay, so surely you have heard about this law, the law of conservation of energy. It's one of those things that people have heard, even though we don't really know what it means. Okay, so this law states that when a particle has some energy, okay, we have a particle here, and this particle has energy E. Okay, when this particle is in a closed system, let's see if you because I said that I was gonna do this in a simple way. Okay, let's try this. When this particle lives in a closed system, I'm gonna explain that in a moment. The energy of the particle will remain always E, will remain constant. Okay, it will not disappear and it will not create more of that energy. For example, let's suppose that this particle at some other point is right here. It moved around a little bit. So at this point, the energy of this particle will also be the same as before. Okay, it will not have diminished nor increased. And at every single point in here, the energy will be the same. The total energy of this particle will be constant. Now, what do I mean by a closed system? This is hard to understand. Well, what is this? A closed system. Okay, if you notice, I drew the particle inside this region in order to try to express that this is a closed system. What is a closed system? A closed system in physics is a system in which the energy is not increased or decreased. For example, if you have a particle falling down on air, okay, like all particles do. Okay, in here, we say that this is not a closed system. Let's suppose that I enclose this particle in a very big box, an extremely big box. I'm talking kilometers uh, on the side, on each side. And there's a lot of air in there, okay? And if this particle falls down, what's going to happen is this, that some of the energy that this particle has at the beginning, when the particle is falling down, some of that energy will be transmitted to the particles of air, to the air, right? And it's gonna heat up the air a little bit. So this is an example of an open system. Okay, this is not a closed system because the energy that the particle had will be getting lost a little, but it will be lost because of the air, because you have air. So this is not an example of a closed system. And in this example, the ball will lose energy, will actually lose energy. It will not conserve its energy. Now let's go to a closed system. Suppose the same box, but I take all the air out. All the air is now out, and this is a perfect vacuum. And I do the same experiment. I place the ball in here, and I let go of it so that it starts to fall down. And whatever energy the particle had at this point will remain the same at all points in this trajectory. Okay, at this point in the trajectory, the energy of this particle will be the same as before, and at every single point the energy will be the same. So in this case, since this is a closed system, now the energy will be conserved. So the conservation of energy for a particle only works for closed systems, okay, which is the kind that we manage in high school. So don't worry. If you just want to understand that the energy is conserved, that's it. That's all you have to understand. The energy is conserved. It is neither destroyed nor created. That is the law of conservation of energy. Okay, and how is this useful? Okay, this is very useful because we can define the following concept. Remember, we have already talked about kinetic energy and potential energy, and we know their formulas. Kinetic energy is one half of the mass of the particle times its velocity squared, and the potential energy is equal to the mass of the particle times gravity times its height above ground. So we know what these things are and we know how to calculate them. Okay, in physics, there is another concept called the total mechanical energy, represented by an E. Sometimes we only say total energy in order not to say too many words. So when I say total energy, I mean total mechanical energy. And this in physics is defined as the kinetic energy of a particle plus its potential energy. Okay, because a single particle can have both of them, okay, not just one of them. For example, try to imagine this. This is the ground, and you have a ball that is already falling down. Okay, it went from, let's say, this position at rest, and it started to fall down, and right here, pay attention to this position right here, the ball is obviously at a distance, at a certain height above ground, so it does have potential energy, and it's also going down. It also has velocity, so it also has kinetic energy. The sum of both is known as the total mechanical energy. K plus U, kinetic energy plus the potential energy of this particle. Okay, so this is a new definition for us, and you're gonna see how this works in a moment, how this is useful. Let's go straight to a problem. Let's suppose this. We have the ground, we have a rock right here, and this rock initially is at rest, and it's, oh my god, okay, that's the best I could do. Okay, originally this rock is at a height of 10 meters above ground, and remember, it's at rest. Okay, so let's right away calculate both the potential and the kinetic energy of this particle. So let's start with the kinetic energy. The kinetic energy is one half times its mass times its velocity squared. Oh, and by the way, I haven't given you the mass. So let's keep it simple. Let's suppose that the mass is 1 kilogram. Okay, so let's calculate the kinetic energy of this particle at this position. So it's going to be one half times 1 kilogram times its velocity squared. But its velocity is 0, right? Because I said that it was at rest. When you calculate all of this, you will get 0 joules. So the kinetic energy is 0 joules at this point because it's at rest. Now let's do the same for its potential energy. Its potential energy is the mass times g times the height. So let's substitute. Its mass is 1 kilogram, g is 9.8 meters per second squared, and the height is 10 meters. When you calculate all of this, I'm gonna give you some seconds, do it. You will get 98 joules. So, oops. So the potential energy of the ball is 98 joules, at this particular location. Okay, now let's find, now that we know these two things, let's find the total mechanical energy, E, which, as you may remember, is the kinetic energy plus the potential energy of the particle. So let's do it. The total energy will be 0 joules from the kinetic plus 98 joules from the potential, and so we have a total of 98 joules of total mechanical energy. Perfect. Now, knowing this will be very useful if, for example, we want to do the following. Suppose that the ball starts to fall down. Okay, so it's falling down, it's falling down, it's falling down. Okay, and you take a snapshot right in the middle. Okay, let's say that you pause the, no, I don't mean pause. Yeah, we take a snapshot. Okay, the ball will remain falling down, but we want to analyze what's happening right at this position in the middle. Okay, right in the middle of the 10 meters. So now at this position, the particle has a height of 5 meters, right? And so we can calculate right there, we can calculate its potential energy at this new position. The potential energy will be, again, the mass times G times H. So let's do it. It's 1 kilogram for the mass. G is the same. And the new height is 5 meters. So calculate this value, please. You're going to get 49 joules. Okay. So at this precise point, we have a potential energy of 49 joules. Okay. Now, suppose that we want to know the kinetic energy of the particle also at this point in the middle of the trajectory. How can we find it? Well, we need 1/2 times its mass times its velocity squared, right? But we don't know the velocity, do we? We know its mass, but I don't know what velocity the particle has at this precise instant. So what can we do? How can we solve this problem? Okay, it's simpler than that. We don't really need the velocity of this particle in order to calculate the kinetic energy. Why not? Because we can make use of the principle of the law of conservation of energy. Pay a lot of attention to how this works. How can I use the principle of conservation of energy? Okay, what I know is this, that the total mechanical energy of the particle was 98 joules at the beginning. And since the total energy is conserved, then at this other location in the middle of the trajectory, we need also that the energy is the same, the total energy is the same as before, okay? Because the energy is not destroyed nor created, it's going to remain the same. Okay, so how can this knowledge helps us to solve this question of getting the kinetic energy of the particle? Well, in this way, what is the total energy? Is equal to kinetic plus potential, right? And we know that the total energy is 98 joules. K, I'm gonna just write it down again. And U, the potential energy is 49, as discovered right here. So I can substitute it. You see? So now we have this equation, 98 joules equals K, the kinetic, plus 49 joules. So this equation allows us to find the kinetic energy at this precise point, even though we don't know the velocity of the particle. So that's really good. How much is going to be K according to this equation? It's going to be 49, right? Okay, so we can write it down right away without any calculations. You see, that's how the principle of conservation of energy works. It allows you to find some energy, either kinetic or potential, if you know one of them and if you know the total energy of the particle. Okay, let's keep going. Let's suppose that the particle has already fallen to this point, okay, which is just 1 meter. uh, I'm gonna erase this line because I want this to look good, and this also. Let's suppose the ball has fallen down up until a height of 1 meter above ground. 1 meter only. And we do the same. We do the same thing. We want to know the kinetic energy of the particle at this point. I want to know this value. Okay? So how can I find it? We don't know the velocity of the particle at this point, but we don't need it. All we need to do is this. Let's calculate the potential energy of this particle at this height. So one more time, mgh, the mass is 1 kilogram, g is 9.8, and the height is 1 meter. Calculate all of this on your own, please, and you will find 9.8 joules, right? So the potential energy at this precise location will be 9.8 joules. Perfect. So how can that help me get this value? Okay, what I do is this. I'm gonna help myself with the knowledge that the total energy still has to be 98 joules. That is, the sum of both kinetic plus potential has to be 98 joules. So let's substitute that. E is equal to 98 joules. I'm gonna ignore the units because otherwise I'm not gonna be able to fit the equation. 98 joules equals the kinetic energy of the particle at this position plus the potential energy of the particle also at this position, which we know to be 9.8 joules. So let's substitute. 98 equals K plus 9.8. And as you can see, we discovered this equation which only has K as a variable, and we can isolate it. So let's isolate it. What do we get? Do it. What you should get is 88.2 joules. Okay? So we have discovered what the kinetic energy of the particle is at this precise moment in the falling without knowing its velocity. You see, that is the cool thing about the conservation of energy. It allows you to do this type of things without really calculating stuff. Okay, so that's how it works, guys. Now let's one more final thing. Suppose that we want to know the velocity of the particle at this precise moment. At this moment, when the particle is right here at 1 meter from the ground. Can we get it? Can we get the velocity? Yes, because now we have the kinetic energy of the particle, okay, which is 88.2 joules. And remember, I'm going to do this with pink. Remember, the kinetic energy is equal to 1/2 times the mass of the particle times its velocity squared. So if I know the kinetic energy of the particle at this point, which is this much, let me substitute that in here. I'm going to ignore the units for simplicity. That's equal to 1/2 times the mass of the particle, which is 1 kilogram, times its velocity squared. And look at this. We have an equation which only contains v as the variable, and we can isolate this variable to find the velocity of the particle at this precise moment. So let's do it. This is going to come out as 88.2 equals 1 half times 1 is 0.5 times v squared. And then we have this 88.2 over 0.5 equals v squared. Do the rest of your own on your own and give me the answer at the end. Okay, you should have find 13.28 meters per second. That's what I got. Let me confirm. Yes, this is what I got. So I could also get the velocity of the particle at this point by using a method of energy, okay? By using the concept that the total mechanical energy is conserved all throughout the falling down, okay? Observe, 98 joules of total energy at this point, 98 joules of total energy at this point, and 98 joules of energy, total energy at this point. So at every single point in this motion, every single point as the ball falls down will be 98 joules. Okay? So that's how these type of problems work.